But here today that saving option is not coming. I don't know. I only posted a meeting, right? Kalyan, catch this meeting. Why? Where is the saving option? Today I didn't get. Kalyan, are you there in the meeting? Are you able
Yes,
to
sir.
see my screen?
Yes, sir, visible, sir.
It is unable to see that saving option. Usually it should come here. Hmm? I only posted meeting. Okay, 1 minute. I
So yes,
rejoined
even
again.
morning we had class, we were not able to record class.
What, ba?
So even morning we had a class, so we were not able to record the class. So I think there's some error.
In Google Meet error or our side problem?
I think Google Meet error, sir. In morning class also, sir was unable to record the class.
Oh my God. Okay. I do one thing. Anyway, I can do screen recorder. I already downloaded the software. Just give me a minute. I switch on that. I start the class. Okay. Okay, guys, very good morning. Are you able to see my screen?
Yes, sir.
Yes. Yeah, we discussed we discussed gear train yesterday, and yeah, we have to start today here. Okay. Now, do you have any doubt in the yesterday class about whatever we discussed? Invalid profile, cycloid profile of the gear tooth, and some of the things we
Clear, sir.
discussed. Yes, tell me, ba.
Clear, sir.
You don't have any doubt? Hello?
No, no doubts from me, sir.
Okay, but thank you. Thank you. Okay. Now, today we discuss the interference, undercutting. These are the important terminology for gear design. See here, what is the interference and undercutting? First, see the theory and give you clarity of the interference and undercutting through some diagram. Okay. A gear tooth has invalid profile only outside of the base circle, right? That's what we discussed outside of the base circle. Now I go back. I think here, yeah, yeah. Whatever we discussed early, see here, this is outside of the base circle. The gear invalid should be designed with from the outside of the base circle. Outside of the base circle. I mean, keeping this my information in mind, very important. Okay. Okay, a gear tooth has invalid profile only outside the base circle. Base circle. In fact, the invalid profile begins at the base circle in some base circle. In some cases, the dedendum so large. Obviously, the dedendum should be. Suppose see here now. This is whatever we discussed yesterday in the invalid. This is the gear profile. Is invalid profile, right? Suppose in some cases, suppose that invalid begins at the base circle, then what will happen? Suppose start from here, then this is going to be a pitch circle, this is going to be a dedendum. The dedendum is so large in this case. Okay. Now, the dedendum is so large that extends the below the base circle. That's what. Now this is base circle. But here the dedendum is starting from here. The base, our profile, tooth or teeth profile starting below the base circle. Hence, the dedendum is so large, then it extend. Then this is extend below the base circle. Okay. Now, in such a situation, the portion of the tooth below the base circle is not invalid. Which portion of the tooth is sitting below the base circle, that is not invalid. Not invalid. Whatever whatever the gear design, the tooth profile sitting above the base circle is invalid curve. Invalid profile. This is below the base circle. It's not invalid. Not invalid. Now see here. Anyway, the tip of the tooth. Take this. The tip of the tooth on matching gear, which is invalid, interferes with this non-invalid portion of the dedendum. Now, for example, see here this figure. See here, this is the whatever we discussed. That invalid is sitting below the base circle. First I complete this. Now, this is the base circle. Base circle of gear, base circle of pinion, sorry. This is the base circle of pinion. Okay, base circle of pinion. Now, the invalid profile of the pinion teeth starting below the base circle. Below the base circle. This is the base circle. This is the sometimes okay anyway control. This is up to this portion is invalid profile. Up to this portion is invalid profile of the tooth. This is invalid profile of the tooth. I mean, which portion extended the gear teeth design below the base circle? That is non-invalid. Non-invalid portion. Non-invalid portion. This is non-invalid portion. This portion. Because this is below the base circle. Now we assumed this teeth from the pinion. This is from pinion. Now the another teeth. I mean, anyway, finally we would like to transmit the power from right one shaft to another shaft with the help of the two gears or combination of gear and pinion. Now we assumed this is a pinion. Now the gear teeth is here. Now the gear teeth is engaged with the pinion teeth now. Now the gear teeth is engaged with the pinion teeth. Pinion teeth, but the gear teeth is perfect invalid. It's started from the base circle. I mean, whatever we are following, that invalid concept, the invalid tooth profile concept applicable for gear as well as pinion, right? Hence, applicable for gear teeth as well as pinion teeth. Now, we initially assumed that the pinion teeth profile. I mean, invalid profile is started below the base circle. I mean, which are the portions are sitting below the base circle? That portion is non-invalid. Above the base circle, we are saying that invalid. But now we are connecting the gear teeth with the pinion teeth, but the gear teeth is perfect invalid design. When the gear teeth is engaged with the pinion teeth, then what will happen? When the gear teeth is engaged with the pinion teeth, now it's going to be disturbing. This is the non-invalid portion. Going to be disturbing in that sense. It will be cutting. It will be cutting. That's what we are saying. The tip of the tooth matting here. The tip of the tooth. See. The tip of the tooth on the matting gear. This is now matting gear tooth. Matting gear tooth. The tip of the tooth on the matting gear, which is invalid, now considered as invalid. The tooth of gear we considered invalid, fully invalid. Now the interfaces with the non-invalid portion of the dedendum. Now this gear tooth now interface with the non-invalid portion of the dedendum when the gear teeth is engaged with the pinion teeth. Now this is called interference. This is called interference. Now the phenomenon of tooth profile overlapping. Now this overlapping and cutting into each other, that is called interference. How it is cutting? Now the pinion is designed, the pinion teeth is designed, some part of the pinion teeth in invalid portion, some part of the pinion teeth is non-invalid portion. But when the gear tooth or gear teeth now is a fully invalid portion, now when this engaged with the or matting or meshing with the pinion teeth, then what will happen? That non-invalid portion going to be overlapping with the gear tooth. Non-invalid portion of the pinion teeth overlapping with the gear tooth. I mean, overlapping with the gear tooth when the gear tooth engaged with the pinion teeth. Now that overlapping and also going to be happen cutting. How it is happening cutting? Now we are transmitting the power. I mean, the multiple rotation going to be repeatedly happening in the along with the pinion teeth and the gear teeth. The meshing or matting function going to happen continuously. Then after some duration of operation, then this is going to be cutting. That is, that overlapping and cutting each other is called interference. When that non-invalid portion is presented either pinion teeth or gear teeth, but when they are functioning, that time that non-invalid gear teeth engaged with the pinion teeth, then overlapping as well as cutting due to some duration of operation, some 1,000 times rotation, or 10,000 times rotation. What will happen? Then obviously it is going to be cutting. This overlapping and cutting process is called interference. Now that's what we are saying. So in this case, the tip of the tooth overlap and digs into the root section. Yesterday we already discussed what is the root section. The tip of the tooth overlaps and digs into the root section of the matting gear or pinion. Okay. Now the interference is non-conjugate action and results in excessive wear. While happening this overlapping and cutting between the two matting teeth, then that will cause us the vibration, unnecessary vibration, wear, and sometimes it may cause us the jamming effect of the two matting teeth. Okay. Now simply, how can we can say in one sentence, when the tip of this is the very briefly you can understand, when the tip of the tooth undercuts the root of the matting gear is known as interference. But as I told you how it is happening, I have been explained how it is happening. Okay, this is called interference. Now, when the gears are generated, the invalid rock cutters. Now, the gear teeth or gear teeth is now it looks like a rock cutters. Then this interference is automatically eliminated because of cutting tool removes the interfering the portion of the flank. Which is where is the flank? We already discussed. This is the face, this is the flank. In the gear we already discussed in the terminology. This is the flanks, this is the space, right? So one portion is flank, another portion is, this is the face, this is the flank we already discussed. That's what we are telling here. The interface is automatically eliminated because of cutting tool removes the interfering portion of the flank. Now after some duration of rotation, because of matting teeth from the pinion or gear, or matting teeth from the two gears going to happen, this is the undercutting. Now the interference going to be removed because the material now removed. Now finally after some 25,000 revolution, for example, the gear tooth profile going to be changed like this. Initially it was interference. After some duration of running or continuous rotation, then finally this shape is formed. Now the interference can be removed, but the strength of the gear going to be reduced. Now this is called undercutting. When the interference removed, now see here, after 25 revolutions, now the gear teeth and pinion teeth will be continuously functioning. But here undercut is happened because of this gear tooth was functioning as a cutter. Based on this non-invalid portion, this cutting going to happen. Removal going to happen because of the gear tooth. Finally, this shape is called undercut. The undercut is weaker. It's going to be reduce the strength of the pinion or gear. Because why I'm saying gear? Suppose if we are considering both are in same gear, okay, reduce the pinion strength here. in this case. Now, undercut not only weaken the tooth, but also remove the small invalid portion. Invalid force. We are removing the material from the using. I mean, not using. I mean, while functioning the two matting teeth. The gear teeth when will be engaged with the pinion teeth, when the pinion teeth is subject, when the pinion teeth is non-invalid portion, that non-invalid portion going to be removed. That is called undercut. Okay. Okay. Now this is due to undercut, the weakens the tooth, but also remove the invalid portion of the adjacent base circle. I mean, this loss invalid profile may be causes a serious problem. I mean, also reduction of the length of the contact also. I mean, this is the. I mean, how can remedy this? How can I remedy this? Eliminate this interference. I mean, undercutting. Why it's happening? Because of the interference. Once we avoid the interference, undercutting not going to happen. When interference is going to happen, sure undercutting going to happen in the gear tooth or pinion tooth. Now, how can I eliminate the interference? Now, increase the number of teeth on the pinion and increase the pressure angle. Use long and short addendum gearing. This way we able to eliminate the interference. Now also see here some of the standard they have given. When we are using 14-point full depth system, 32 teeth will be suitable for it, may avoid the interference. When we are using 20-degree full depth system, for using 17 teeth, it may avoid the interference such a way that we can avoid the interference. Yeah, I thought to show you. Yeah, see here. Yeah, see here. I might have been told you early. I missed out. Anyway, no problem. Now I tell you. Now see here. This is a gear. This is the pinion. Now the gear is rotates and engaged with the pinion. Now suppose the gear. Now some students may not understand. Now this is invalid. Extended, sorry, whatever we discussed, invalid, non-invalid in the pinion side only. Now this is invalid extended in the below the base circle. Below the base circle, invalid extended. Okay. Now what will happen when the gear rotates? Slowly removing the material. Now, due to this is a causes the interference initially. When it is continuously functioning, the gear teeth going to be slowly remove the material based on length of the gear, based on the length of the gear tooth. Then slowly remove the material. Finally, it's going to come such a way of design here. This is the now undercutting. This portion is now undercutting. Now see here. Now this portion is undercutting. So that undercutting happens due to interference. If we avoid the interference, the undercutting can be automatically solved. The problem can be solved automatically. Okay. Now we come to this. Get to the failures. Now, what are the failures? Now, I mean, there are two basic methods of the gear tooth failure. One is breakage of tooth due to static and dynamic loads, and I mean gear tooth failure based on the surface destruction. Okay, the complete breakage of the tooth can be avoided by adjusting the parameters of gear design. I mean, by adjusting the parameters module and face width of the gear teeth. Model and face width of the gear teeth. Now, I mean, the complete breakage of the tooth can be avoided by adjusting the parameter of the gear design, model and face width. You may expect this kind of questions in the objective. Now, model, gear, I mean, face width is nothing but B is equal to 10 times of model. Okay, so that the beam strength of the gear tooth is more than the static and dynamic load. I mean, beam strength is greater than this summation of static and dynamic load. that can be avoid the failure of the tooth. Okay. Now this is also we are going to discuss further later. What is the beam strength? What is the wear strength in later? Now just keep in mind the surface destruction. Now second one is surface destruction. The surface destruction or tooth wear is classified according to the basis of the primary causes. What are the primary causes? There are different types of wear: abrasive wear, corrosive wear. I mean, these are the under the category of surface destruction of the tooth surface. Okay. Now, first we see this abrasive wear on the tooth surface. I mean, the foreign particles in the lubricant and such a, the foreign particles in the lubricant in such a that dirt, rust, weld spatter, metallic debris can scratch the tooth surface. Okay, how can I remedy this? How can I remedy this issue? How can I resolve this issue? Then we have to remedies against this type of wear. Provide the oil filters, appropriate oil filters, increasing the surface hardness, and use high viscosity oils. When we are using appropriate oil filters and increase the surface hardness and high viscosity oils, can be avoided this abrasive wear. Abrasive wear. They have given some explanation. Thick lubricating film developed by these oils allows the fine particles to pass without scratching. When we are using thick lubricating oil, whenever foreign particles entered, the micro particles are entered, with the help of this thick lubricating oil, that foreign particles cannot scratch on the surface of the gear tooth. Okay, that's what they are suggesting. Use thick lubricating film. Sorry. Okay, we are going to discuss this thin film lubrication, thick film lubrication. We are going to discuss in the next topic. Bearings. Okay. Now corrosive wear. I come to corrosive wear. The corrosion of the tooth surface is caused by the corrosive elements such as extreme pressure additives present in the lubricating oil and foreign materials due to the external contamination. These are the parameters causing the corrosive wear. How can I remedy this? How can I resolve this problem? Now these elements, whatever this extreme pressure additives and foreign particles, these elements attack the tooth surface, resulting wear uniformly distributed over the entire surface. How can I resolve this problem? Then we have to providing this complete enclosure, appropriate enclosure for the gears, free from the external contamination. Selecting the appropriate additives and replacing the lubricating oils in proper time interval, that can be resolved the corrosion wear on the surface of the gear tooth. Now I come to this. Now initial pitting, because initial pitting, destructive pitting. Initial pitting is the corrosive pitting is localized phenomena. This is characterized by small pits and high spots. Small pits and high spots presented on the surface of the tooth. Okay, such a high spots progressively worn out. And the load is redistributed. When the high spots presented on the surface of the tooth surface, it will be progressively worn out and the load is going to be redistributed. Then initial pitting is occurred by this error of. What are the causes here? What are the parameters for happening initial pitting? Initial pitting is caused due to the error in tooth profile. High spots are created. Why? Because of error in tooth profile and surface irregularities and misalignment between the gear teeth and pinion teeth. This is the causes for initial pitting. How can I remedy this? How can I resolve this problem? Now, initial pitting or precise machining. The remedies against the initial pitting. We need a precise precise measuring of gears, adjusting the correct gear, adjusting the correct alignment of the matting gears. I mean, alignment of the pinion and the gear. Okay, and then the load is uniformly distributed across the full face width of the gear. Then it can be reduced the dynamic load. Now, destructive fitting. Destructive fitting is the surface fatigue failure. This is surface fatigue failure. Okay, I mean, which occurs when the load of the gear tooth exceeds the surface endurance limit. These are very simple, you can easily understand. I mean, which occurs when the load on the gear tooth exceeds the surface endurance limit. I mean, the surface of the gear tooth exceeds the surface endurance limit, endurance length, then it will be creating the problem. That is called a destructive pitting. How can I resolve this problem? I mean, anyway, this type of failure is characterized by pits which continues grow, resulting in complete destruction of the tooth surface. And some cases, I mean, sometimes it may causes the breakage of the tooth. Sometimes, so destructive pitting, very important consideration. We have to. How can I resolve this problem? Anyway, I mean, destructive pitting depends on the number of stress cycles. Depends on the also the destructive pitting also number of stress cycles. Please go through this. You may expect 1 or 2 questions from this objective questions. Okay, this type of, I mean, destructive fitting, I mean, the failure can be avoided by designing the gears in such a way that, I mean, see, wear strength of the gear tooth is more than the sum of the dynamic and static loads. We already discussed. I mean, bending strength must be greater than the summation of the static and dynamic loads. Similarly, our wear strength also must be greater than the sum of static and dynamic load. Then it can be avoided. This is a destruction fitting. Okay. Now the surface endurance limit can be improved by increasing the surface hardness. And the surface of the tooth we can go for some hardness process. That way also we can avoid the destruction fitting on the surface of the tooth. Now I come to scoring. Scoring is excessive surface pressure. Excessive. What are the causes? What are the parameters for creating the scoring? Excessive surface pressure, high surface speed, and inadequate supply of lubricant that can result in breakdown of the oil film. Okay, the results in excessive frictional heat. This is also excessive frictional heat. When it will happen, excessive frictional heat, I mean, if you are not using proper lubrication, if you are not using proper thickness, I mean, lubrication film or appropriate type of lubrication, then excessive frictional heat going to be generated. Overheating of meshing teeth, what happened? I mean, overheating of the meshing teeth. I mean, this process going to happen continuously. Then in between two teeth surface, the matting teeth surface going to be stick slip phenomenon is nothing but it looks like the teeth matting teeth are going to be sticking, or alternate welding or searing takes place due to high spots at high temperature. Okay, then what is the remedies? How can I avoid this? Selecting the parameters such as surface speed and surface pressure and proper flow of lubricant and appropriate film of lubricant is important to resolve this scoring problem. Okay, scoring issues. Okay, now we come to, do you have any doubt? Please go ahead. Whatever we discussed now, because now we are entered into this force analysis. Then later, once complete this, when we are going to enter into the, gear design based on beam strength, then later gear design based on wear strength. So whatever, if you have any doubt, please go ahead. I can clarify it and we can move to this content. Hello? Shall we move to this?
Yes, sir.
Okay. Now, first we discuss the force analysis. Okay. I mean, already we discussed some of the content while designing the shaft, because in the shaft, whatever we discussed earlier, first chapter, the gear was connected in the on the shaft for power transmission, right? Based on the gear, radial load and tangential load, we considered, right, horizontal bending moment and vertical bending moment. Based on horizontal and vertical bending moment and torque moment from the twisting, amount of torque transmitted by the gear, these are the parameters we used in the shaft design. Horizontal, tangential load, radial load we considered for finding the horizontal bending moment, vertical bending moment. Then we considered, resultant bending moment from the horizontal and vertical bending moment, the resultant bending moment, and a torsional moment, amount of torque transmitted by the gears. Then these two parameters we used to define or design the shaft dimensions in the early chapter. Now, similarly, we are going to discuss how much force is acting in the teeth, because here the teeth design is very important, crucial, the very important part of the gear, very important part of the gear. That is, it depends on force, how much force acting in radial direction, how much force acting in the tangential direction. Okay, that's all. The gears, the power is transmitted by means of the force exerted by the tooth, obviously. Yeah. What will happen? The force is exerted from the tooth. See here, this is maybe a driving gear, this may be a driven gear, or vice versa. But one teeth is exerted force on the other teeth, then the power is transmitted. Now that's what we are going to do, the analysis of force here. Okay, see this figure now. This is the Pn. The Pn is resultant force. The Pn is nothing but resultant force acting on the pressure angle. As I told you, that pressure angle alpha we discussed already. From the alpha, the resultant force always acting through the pressure angle. Now the resultant force Pn is acting through the pressure angle. Then this resultant force, any resultant force, it can be resolved into two components. One is vertical component, another one is horizontal component. The vertical component we are considering here radial force, and the horizontal component we are considering here tangential force. Vertical force, the radial component we are considering vertical, the radial force we are considering vertical component. The horizontal component we are considering the tangential force in our gear design. Okay, that's what. Now the tangential, that's what here telling clearly, the tangential component PT is useful for the load. Because of this, it determines the magnitude of the torque. Now, the tangential torque. Now see, anyway, the tangential force is used to define our how much amount of torque is transmitted. This is a tangential force, right? What is the tangential force? Here P, for example, PT. What is the torque transmitted? What is the radius of the gear into d by 2, right? The tangential component. Based on the tangential component, we are able to understand how much torque is transmitted. But in radial component, what is use of radial component? When this gear is going to be mounted on the shaft, during that time radial component also important for designing the gear. Okay, that's all. Okay, consequently the power transmitted the radial component. Now whatever we discussed earlier, this is a common normal. This is a common normal. In this common normal, the Pn is passing. The resultant component always acting in the common normal. At which angle? Alpha. That is nothing but pressure angle. Okay. Now this is already we discussed. This is a pitch point. This is a driven gear. This is a driving. Pinion gear. Now the PR is now nothing but radial force. This diagram says that our gear. Schematic force diagram with respect to gear schematic sports diagram with respect to pinion. The top one is now this is rotating in this direction. When it is rotating in this direction, then this force is PT is towards right hand direction, rightward direction, towards rightward direction. The radial force towards our downward direction. When this is the now when this is rotation in the clockwise direction. When this gear teeth engaged with the pinion teeth, what will happen? The force PT is going to be acting this direction, then PR going to be acting upward direction. Now see here, this PR in the gear, PT in the PR in the gear downward direction, PR in the pinion in upward direction. Now the summation going to be satisfied with the our mechanical equilibrium condition. Now the PT here, the PT is this direction, rightward direction. Here the PT in leftward direction. Now obviously the summation of the force going to be satisfied with our mechanically equilibrium condition. The resultant force going to be satisfied with our equilibrium condition. Now this is in opposite direction. This is a clockwise direct rotation of the gear, and the pinion is rotating in anti-clockwise direction. Now I come to this derivation. Now see here, the torque transmitted, whatever we discussed, mt is equal to p into d by 2. The d dash is nothing but our pitch circle diameter. If we consider the d dash in pinion, you can put d subscript p dp. Suppose if you are considering from the gear, you can put p into dg subscript g divided by 2. That is nothing but our torsional moment, torque, amount of torque transmitted by this mechanism. Okay, now I come to this. What is a PT and PR? PR by PT is equal to tan theta. This is very basic information. Now PR by PT is nothing but tan alpha. Tan alpha. From this relation, we are able to find out what is a PN. What is PN from this relation? I mean, we know this. This is alpha. This is a PN. This is PT. This is a PR. From this relation, we are able to find out this PN also. PN is nothing but, if you know the PT, if you know the pressure angle, then PT divided by cos alpha. PT divided by cos alpha. Now this is PT by cos alpha. Now I would like to write my equation in terms of I can write in my equation in terms of resultant load. The PN is nothing but resultant force. Okay, now here mt is equal to d by 2 into d by 2 into pn into cos alpha. I can write my equation, my torsional moment with respect to based on PR as well as PT also. Okay, now the above the force analysis, what are the assumptions we are considering here in this? Very important assumptions we have to understand first. What are the assumptions we considered while defining the force analysis of the gear teeth or pinion teeth? What are the assumptions we are considered? See here. As the point of contact moves, the magnitude of resultant force Pn also changes. Now see here. Now that's what I put this video here. Now this is a contact point. Sorry. This is the contact point of the gear. This is a contact point. But the contact point changes. It's while running dynamic condition, the contact point just changes slowly. For example, the gears are running, both gear and pinion are running, rotating slowly. Then the contact point, each gear going to be messing with the same contact point, but due to rotation, this slowly changing. Then what will happen? The resultant force also going to be slowly changing, but the maximum resultant force acting at the corresponding pressure angle only. But in this case, we are not considering that effect here. That's what we are telling here. At the point of the contact of moves, the magnitude of the resultant force of Pn changes. This effect we are neglected. Okay. Now it is assumed that the one pair of the teeth takes the entire load. Now see here in this design also we are assumed that one pair of teeth engaged, one pair of teeth shared entire load. See here, Is there, I mean, at a time, is there engaged with any two teeth? No, only one teeth is engaged always. That's what we are considering here. At a time, I mean, it is assumed that only one pair of teeth takes entire load. Okay, entire load. At the times, there are two pairs which are simultaneously in contact and share the load. Now, our calculation, we considered this. But once this teeth, engaged and disengaging, the other teeth immediately coming into contact. That's what we are telling here. At the times, there are two pairs which simultaneously contact, engagement and disengagement, engagement and disengagement. But maximum load considered, maximum load will be shared in the one teeth only. That's what we are considering the calculation one teeth only. Okay. The analysis valid for the under the static condition. Now we are considering the static condition. Why we are considering the static condition? I mean, for example, at the static condition, it will take more amount of force for the initiation, for the initial transmission of the power. For example, train. While train is in railway station, right? But when it is running condition, it won't take more torque. It won't take more power. It won't be consumed more power while running condition. But at the starting condition, it will take enormous torque. It will take enormous force. And that's what we mean. Actually, we are considering a static condition. In static condition, the initiation of torque will be more as compared to running torque, running force. Hence, we are considering the analysis or under the static condition when two gears are running at very slow velocities. I mean, later we are going to consider a dynamic load also. We will discuss later that, okay? But initial condition, we are taking like that. I mean, when we are going to discuss in beam strength, the gear design based on beam strength, gear design based on wear strength, we are going to be considered some of the dynamic loads, okay? And in practice, dynamic force in addition of the force due to the power transmission, the effect of the dynamic force neglected in the force analysis. Okay. So anyway, now we know this MT we can define through this way also. Suppose MT we can define through power is equal to 2 pi NT. 2 pi NT here, NT is nothing but MT divided by 60 e power 6. E power 6. This is N is our speed of gear or speed of pinion. Okay. This is our amount of torque transmitted. From if we know how much power we would like to transmit, we are able to find out MT. Okay, if you know the speed of the gear or speed of the pinion, because the power is, I mean, how much torque transmitted by the gear and how much amount of torque transmitted by the pinion will be same. Only the velocity is changing. NP or NG we are going to consider. Then remaining things, whatever we discussed earlier. See, this is the from this gear design we are able to find out. This is from the general formula. Okay, so PT is equal to 2 MT divided by dP. Suppose based on gear, it may be 2 MT divided by dg. This is tangential load. From this also, we are able to find out our what is PT. Once we know PT, once we know PT and alpha we know. Once we know PT and alpha, we are able to find out PR or we are able to find out PN also. Now I come to the force free body diagrams. Now whatever we discussed, just to go through that, you can get it. See here. Now it is assumed that this pinion is driving in driving element. The pinion is now assumed to be a driving element, and the gear is now driven component. Now here the pinion rotates in clockwise, anti-clockwise direction. The gear rotates in clockwise direction. Okay. In running condition, the point pinion point P and gear point 1 is assumed to be the radial load. Okay. Now the second diagram represents that when it rotates, pinion rotates in anti-clockwise direction, and gear rotates in clockwise direction. The radial load, sorry, tangential load. This is radial load here. Here a tangential load in opposite direction. For maintaining the equilibrium condition, this must be in opposite direction. The summation of force must be satisfied the mechanical equilibrium condition. Okay, now this now this is a combination of this is a schematic free body diagram of the schematic diagram or free body diagram of the force analysis. This is now coupled to this A and B. This is the vertical force, radial force, and horizontal force, the tangential force acting in the pinion in the gears, such a way that you can understand. Okay, this is very simple. Okay, now I come to the beam strength of the gear tooth. Now we entered into the more gear design concept. First, we are going to discuss the concept about the concept. First concept of beam strength. Second concept is wear strength. Okay, this is the guy Wilfred Lewis. He did research and he published in his research paper about the analysis of bending stress in gear tooth. He published this work in 1892. Till today, a Lewis equation, Wilfred Lewis equation, we are using for the gear design. That's what we are telling here. Till today, Lewis equation is considered for the basic equation of the gear design. Okay. Now, what is the key information? What is the key concept he assumed? In this Lewis analysis, he assumed that the gear in the form of cantilever beam, the gear tooth, he assumed that in the form of cantilever beam concept. Now, see here, now the cantilever concept, cantilever beam concept. Now the PT causes the bending moment. I show you later. In the next page, you can understand how the bending moment is generated while considering the gear teeth as a cantilever beam. Okay, the Lewis equation based on the following assumption. He also followed some of the assumptions we have to understand. Then only we can clearly understand the whole concept. The effect of radial component PR, which induce the compressive stress. Obviously, the effect of radial component which PR is induced the compressive stress. He neglected that radial force component PR. And also now he assumed that the PT, the tangential components, is uniformly distributed over the face width of the gear. Obviously, what is the face width of the gear? The face width of the gear is two matting gears are engagement and disengagement going to happen. Now this is the face width of the. This is the face width. This is the what is this? This is now pitch circle diameter. Now this is the face width. Okay, that's what we assumed, that the tangential component PT is uniformly distributed over the face width of the gear, this region. Okay, this is the possible. This is a possible when the gears are rigid and accurately machined. This is a possible rigid in that sense. It should be properly connected. It should not have any vibration. It should not have any jamming during operation. Okay, that's what the gear should be rigidly positioned. Fixed and accurately machined. The matting teeth of the gear or matting teeth of the pinion must be machined in accurately. Okay, the effort of stress concentration. As I told you earlier, the stress concentration neglected in this because of we are providing this special special fillet radius design in the corner surface. Then he assumed that the stress concentration is also neglected. Okay. Now, in his calculation, he always considered only one pair of the teeth in contact, while transmitting the power. These are the assumptions. This very simple concept you can easily understand. Now the maximum tangential force at PT, that I mean that the tooth can transmit the bending, transmit the torque without bending failure. Without bending failure, there is a beam strength. Now, what is this? We will see that one by one. Now see here the gear teeth. Now this is maybe pinion teeth or gear teeth is considered. Now this is the radial, the tangential load acting at the teeth surface, I mean face width of the teeth. But he considered in his design, in his concept, he considered the tangential load. I mean, whatever we already discussed, the tangential load, nothing difficult one. The tangential load acting on the edge of the teeth. Now this side, the teeth is now looks like fixed. Now this is the fixed. Now this is a cantilever beam. Looks like cantilever beam. This height is the height of the teeth. Assume that the length of the cantilever beam. Now the load is acting here. Now where is the weakest region? Okay, I mean this is the x-axis, the weakest region. I come to that point later. Okay, that's all. The tangential force PT is a causes the bending moment. The cross section of the teeth varies from free end to fixed end. Now this is assumed that a fixed end. Okay, this is assumed that a fixed end. This is assumed that a free end. But the gear tooth profile, the gear teeth profile is varying. Hence he constructed such a way that a parabola, varying cross section, because varying cross section means we cannot avoid, because we would like to provide a perfect invalid profile, then only we can avoid we can follow the our law of gearing. Hence finally he assumed that this is a parabola constructed within this tooth profile. Now this is a dotted line. Why this is the weakest section? He pointed out this is the weakest section, or I mean region of interest. Please tell me why this section X is weakest section or region of interest he assumed in his concept. Please. Yeah, please someone tell that. I'm sorry, Jayesh, Amarnath, Kalyan. Someone reflect, boss.
Sir, maximum bending moment.
Yeah, thank you, but thank you. Who is this?
Abhilash.
Thank you, Abhilas. Because I'm in presentation screen mode, so I am unable to see your name and who is talking. Thank you. Okay. Now this is the region maximum bending moment. Hence we are considering as a weakest section or in region of interest. Because later you may ask that, sir, this cross section we are saying that the varying, I mean parabola, then how you are considering this I is equal to BDQ by 12 uniform cross section area? Like that you may ask later question, because this is the weakest region, hence a corresponding this dimension we are considering for our polar moment, I mean for our moment of inertia calculation. Okay, now come to the bending moment. I mean MB is equal to P1 into PT into height, PT into H. This is the maximum bending moment, right? Now, I mean here moment of inertia is nothing but the weakest cross section, corresponding weakest region, corresponding cross section is B. I mean B and T. This is the T thickness. This is the B. Based on that, the BD cube by 12, BT cube by 12, and Y is T by 2. These are the things, parameters required for finding the bending stress. Now we know there's a governing equation of governing bending equation. Now sigma B by Y is equal to MB by I. From this relation, sigma B is equal to MB into Y divided by I. Substitute these two relations. Finally, we are going to get like this. Okay. Now, Now see here, this is finally we are going to get this relation sigma b bending stress. From rearranging this equation, our aim is to find out the PT tangential load. What is the tangential load? PT is equal to B into sigma B into T squared by 6H. This is our tangential load acting in the end of the teeth. Now see here, now I'm not going to change the equation. Just I would like to add the m numerator and denominator. Hence, the equation value doesn't change. Now m into b into sigma b into t squared divided by 6hm. Now this is I introduced m is nothing but our model. Okay. Now m b sigma b into t squared by 6hm. Now this t squared by 6hm, this is nothing but a factor. This is nothing but factor. See here, numerator is the meter square, millimeter squared, or denominator also millimeter squared. This is assumed that the factor, this is the Levy's form factor. The guy who developed the concept, he introduced the factor y, that is nothing but Levy's factor. Levy's factor. Now, this is simply I can write PT is equal to MB into sigma B into y. PT is equal to MB into sigma B into y. Now, this is a very important equation. Now, okay, okay. Yeah, for our understanding, suppose if you have any doubt, I would like to explain. That's what I put this figure here. Otherwise, nothing. Okay. Now, PT is equal to MB into sigma B into y. Now, this is the y is called our Levy's form factor. Okay. Now, the equation, whatever we discussed, the equation, this equation, PT is equal to MB into sigma B into y, we would like to understand this sigma B now. Now, the relationship between the tangential force, we have written the equation PT, relations between the tangential force and bending stress. Bending stress and teeth design, right? But see here, what is the variable parameter here? Once the gear teeth is designed, then M is constant, B also constant, Y also constant. Only the variable parameter, while increase the load or decrease the load, the sigma B is going to be varying, because sigma B is only varying parameter, right? That's what we would like to say here. I mean, then when the tangential force increased, the stress also increases. Remaining parameters are constant. Constant in that sense, once we designed the appropriate, dimensions of the gear teeth, for M is followed as per the table, B, width of the gear teeth followed as per the table, and Y also followed as per the table. Finally, which one is variable parameter? While increasing the tangential load, the bendings is going to be increasing. Reduce the tangential load, the bendings is going to be decreased. Hence, now, based on that concept, now I am increasing my tangential load up to permissible stress value. Now, what I am doing here, now I am increasing my tangential load. Now, I am increasing my tangential load PT. I am increasing my tangential load PT for increasing the sigma B up to permissible value. When I am increasing PT up to permissible value of sigma B, when the sigma B reaches permissible value based on my increment of PT, finally that PT I am considering that SB. SB is nothing but corresponding to sigma B permissible value. Now, this is beam strength. Very simple. Instead of PT, I am putting SB, beam strength. But I am giving the reason. I'm giving the reason. But while discussing this concept, are we discussed our applied PT is maximum limit or less value? We never discuss. That's what I'm giving here explanation here. Now I'm increasing PT. Other parameter, once the gear is designed, MB and Y are constant. Only the variable parameters, bending stress. When PT is increased, then bending stress also increased. When the PT we are increasing up to the permissible value of sigma B, up to the permissible value of sigma B, we are increasing the PT. That PT is called beam strength, SP. That's what we are telling here. I mean, the corresponding force PT is called beam strength. When the stress reaches the permissible magnitude of bending stress, the corresponding force, I mean, PT is called beam strength. Okay, beam strength. We are giving the new notation sigma B. Sorry. Sigma B is the maximum value of tangential force. Sigma B is the maximum value of tangential force. Sorry. Sigma B is the maximum value of tangential force that the tooth transmit without bending failure. Also, the tooth should not be failure. Okay. Now replacing PT instead of SB. Now SB is equal to, this is our valid equation. SB is equal to MB into sigma B into Y. Now this is the, I mean, Y is already told you now. I mean, Levy's form factor. I mean, sigma B is a permissible bending stress. SB is bending strength. Bending strength. Now I come to this further more information here. Now the equation, whatever equation we discussed, this 17.16 is known as Levy's equations. The values corresponding to the Levy's equation, the values of Levy's factor Y is corresponding to the 20-degree full depth. 20-degree full depth, because we already discussed it. I mean, 20-degree full depth, we can avoid the interference also. Hence, we designed based on the 20-degree full depth. Now, here the another guy entered in this work. That guy name is Earle Buckingham, right? He suggested that endurance limit stress of the gear tooth approximately 1/3 of the ultimate tensile strength. He gone to research. Then he came with the another information. The endurance limit stress of the gear tooth approximately 1/3 of the ultimate tensile strength of the material. Now, he found this equation. He only formulated the equation. I mean, that guy Levy's, but some modification. Yes, that Earle Buckingham introduced some modification based on the endurance limit stress of the gear tooth. Then he found that he gone through some research, and finally he found that the sigma B is 1/3 of sigma B is equal to, I mean, SE. The sigma B bending stress is equal to endurance limit stress is equal to 1/3 of the ultimate strength. 1/3 of the ultimate strength. Suppose in your problem we are not giving bending stress. Suppose if we are giving only ultimate strength, you have to follow this design procedure. I mean, sigma, you have to follow this permissible stress value sigma B is equal to SUT divided by 3. Ultimate strength divided by 3. Okay. Now, I come to this some of the conclusion now. I mean, for avoid the failure, that SB, the beam strength must be greater than or equal to effective load. What is the effective load? We will discuss later. Up to now, we discuss only bending strength. The effective load we will discuss later. Now, some discussion here. I mean, SB is equal to M into sigma B into Y. Now, as I told you, M, B are same for the pinion and gears, right? That get the whatever, the size of the gear, bigger or small, but the teeth invalid, the tooth invalid must be same, right? That's what we are considering. M, B are same for the pinion as well as gear. Then what is the difference? Means from this equation, from this equation, M this M, B are same for the pinion and gear. I mean, this is why. I mean, what is the remaining parameter? Yes, B is remaining parameter. I mean, remaining parameter proportional to sigma B into Y. Sigma B into Y, right? That will decide the strength of the pinion or strength of the gear. Because these two parameters are same. Only sigma B and sigma Y will be varying. Sigma B, why it will be varying sigma B? Suppose I am using two different material, pinion one material, gear another material, sigma B is varying. That's what we are saying, that when the two materials are used, when the different materials are used, the sigma B and Y decides the weaker between the pinion and gear. This will give you which one is going to be weaker in our design, either gear or pinion. Now, I mean, anyway, come to the conclusion. The Lewis form factor always less for pinion. Lewis factor always less for pinion, because see here, this is Lewis form factor always less for the pinion, because now less for the pinion. Hence, when the Lewis factor less for the pinion, if we consider both are same material, obviously pinion going to be, the pinion is going to be a weaker than the gear. Lewis factor same for, if I'm considering Lewis factor same for gear and pinion, Lewis factor sigma B into Y, Lewis factor I'm considering same for pinion and gear, then in this situation the same material also used, then pinion is the always weaker than the gear. You may expect this type of one more questions. Now see the table. The value for the Lewis factor for Y, Lewis factor Y for 20-degree full depth invalid system, invalid gear for teeth profile. Now suppose teeth profile is that the number of teeth 15. This is Lewis factor. Number of teeth, suppose I am considering 26. Now 26.344. This is Lewis factor. Now see here. Here this Lewis factor is less for always pinion as compared to gear, but same material. Then pinion is less strength. Pinion is weaker than the gear, because see here, pinion is, the size of the pinion is smaller than gear. Number of teeth also going to be less compared to gear. And suppose the gear is, the pinion is 18 teeth are presented, 18 tooth are presented, then corresponding that the Lewis factor is the 0.308. Suppose I'm using the gear is bigger than the pinion, then suppose this is, now I'm using some 24 gear. Now 24 number of teeth on gear, then Lewis factor is higher than the 18 teeth of the pinion. Hence, based on this equation, finally, even same material, the Lewis factor is less for pinion, Lewis factor is more for gear. Hence, the pinion strength is weaker, strength is less than the gear strength. Hence, pinion is weaker than the gear. Please, this table also given will be providing you for this gear problem. Now, I come to this, some of the, therefore the maximum bending stress equal to endurance limit stress already we discussed. Now, what are the factors? What are the factors for improving the endurance limit factors? One is improving the surface finish of the gear tooth, size of the gear tooth, increasing the size of the gear tooth, reliable design, and avoid this stress concentration, right? Now, these are the factors can be improve the endurance limit strength, endurance limit stress. Okay, now I come to the effective load calculation, effective load on the gear tooth. See, earlier we discussed, just I told you that the bending strength SB, we know the reason, what it is, how it came, we know that. But greater than or equal to effective load. Now, what is effective load? We never discussed. Now we discussed that. What is effective load? Now, this is the information we already discussed. PT is equal to 2 mt dot by d dash. I mean, it may be a gear teeth, it may be based on pitch club gear or pitch club pinion. Now, this is from standard governing equation P is equal to 2 pi divided by 60. நான் கால் பண்றேன் ஒரு 10 நிமிஷம் இருப்பா. Okay, now see here, this is now the value of the tangential component that depends upon the rated power and rated speed. In gear design, maximum force, we are considering the gear design maximum force criterion. I mean, maximum force criterion due to maximum torque transmission. We are introducing the another factor, service factor. Service factor CES. I mean, that service factor is nothing but now MT max divided by MT. MT max, it's the maximum torque transmitter. This is the torque transmitter. I mean, we will discuss later. This is nothing but MT is nothing but our starting torque. The starting torque. This is a rated torque. I mean, this is a starting load. This is rated load. Okay. Now we are introducing service factor CS for finding our effective load. Anyway, we not yet completed. Now there are two methods we are going to consider for finding the effective load on the gear teeth. Effective load on the gear teeth. The first one is approximation of. The first one is now. Sorry. The first one is approximate estimation. Yeah. The first one is approximate estimation by the velocity factor in the preliminary stage of gear design. Okay, for the precise evaluation or design of the gear. And second one is by Buckingham equation, the final stage of gear design. This is second stage. What is the Buckingham equations? We will see later. Okay, now first stage. It is difficult to measure or evaluate the exact magnitude of dynamic load in the preliminary stage. Actually, in the gear design, very difficult to evaluate the exact magnitude load of dynamic load, exact magnitude of the dynamic load in the preliminary stage of gear design. Okay, to overcome that issue, we are introducing the velocity factor. In that sense, the people gone to research and they are introducing the velocity factor to overcome this calculation, dynamic load calculation. Based on this speed, it can be defined the velocity factor. Now see here, I mean, that to overcome this difficulty of this dynamic load evaluation in the preliminary stage of the gear design, the guy introduced velocity factor. His name is Barth. He might have been gone to number of research work, and it might have been verified in the laboratory as well as practical applications. Finally, the scientific community agreed with use his formula. CV is equal to, CV, velocity factor for, instead of finding dynamic load condition, we are using velocity factor, whatever he introduced. For ordinary and commercially cut the gears made with form cutter, while preparing or making the gear with form cutter, and the velocity of the gears is, V is nothing but pitch velocity. Pitch line velocity is 10 meter per second, less than 10 meter per second. We are using this formula for finding the velocity factor. Already we have discussed about the service factor. Keep in mind, now we are discussing about velocity factor. Similarly, for accurately hopped or generated the gears, some other way of method, accurately hopped and generate the gears, but the gear speed is now less than 20 meter per second. The speed of rotation is at 20 meter per second velocity, pitch line velocity. Then we are using, velocity factor CV is equal to 6 by 6 plus V. I mean, similarly, if the gear, for the precision gear making the gears in precision, I mean, sorry, for precision gears with the shaving and grinding and lapping operations, during that time, the gear rotation is based on that. Based on this operation, during that time, the gear rotate, I mean, the pitch and velocity is the 20 meter per second you consider. Finally, this is CV. Velocity factor is equal to 5.6 divided by 5.6 in plus root V. I mean, this is the guy introduced by him. I mean, this is verified, and finally we are using this concept directly. Now, if we want to know the reason, we have to go through his papers, you can understand. But I tell you one thing, now why we are not discussing those things? Because this is already proved it. Directly we are taking, because, I mean, for publishing one journal paper, it will take at least 3 to 4 years. But how many years he did research, we do not know that. But straight away we are using that. Suppose if you want to go for modify this equation, then you have to go for the research. That is your next level of studies. You may go for MS or PhD. If you may not complete even MS, then you can go for PhD. Then you can overcome this concept. Then you have to prove it. You have to prove it, and you have to do a lot of experiments in laboratory as well as practical. Finally, you can define your own equation for, I mean, velocity factor. For initial stage of dynamic load, very difficult. Instead of that, we are using velocity factor. Okay. Now, finally, I come to this. Now, what is the velocity factor? Here, this small v. Small v is, I told you, that pitch train velocity in meter per second. Now, we know that pi d n divided by 60. This is from the d, and it is the speed of the gear or speed of the pinion, or d is nothing but speed or pitch circle diameter of the gear or pinion. From this, we are able to find out the pitch train velocity v. From this, now finally I come to this. Effective load is nothing but CS by CV into PT. CS by CV into PT. This is called effective load. You may expect this kind of question in your objective. Even okay, this is any one parameter will be given. You have to find out PT or P effective load, okay, or tangential load, okay, CS or CV. Suppose that, I mean, suppose radial load will be given to you, and pressure angle will be given to you. You are able to find out effective load, but the CS-CV ratio may be given to you. So, yeah, I mean, multiple ways we can ask simple questions from this. Okay, now when the gears, okay, yeah, I thought, okay, anyway, yeah, when the gears rotate very low speed, almost zero velocity, the transmitter load PT can be considered. Anyway, this is the whatever we discussed information only. When the gear rotates very low speed, almost zero velocity, the transmitter load PT can be considered to be the actual force present between two meshing teeth. Axial force present between the two meshing teeth. This teeth and this teeth when engaging this teeth and this teeth. Okay. However, the most of the case, the gear rotates an appreciable speed, and it becomes necessary to consider dynamic force. Now we are entering into the dynamic condition, dynamic load, how it will be introduced.
Sir, it's already 11:30, sir.
Okay, I complete this.
Yeah,
this
another
is,
class at 11:30.
okay, okay, I agree with you. I complete only this page. This page only just 2 minutes, please give me. I complete it. Okay. Okay. Now, when see here, our the most cases why we are not very difficult to understanding the dynamic load. That is the reason I would like to tell you here. I mean, when here see here, when the gears rotates in appreciable speeds, it becomes necessary to consider dynamic force. Here see here, when this gear is entering now this gear is entering, right? This gear entering. Now, when it will be a dynamic condition, it may create the impact force. Impact force. Why that impact forces are creating? What is the reason? We have to understand. See here, what is the reason and why we are unable to track this dynamic load here? I mean, how the impact force are creating between the meshing teeth. This is the reason inaccuracy of tooth profile. See here, now this gear is engaging. Suppose more gap is there. I mean, it may come backlogs, as whatever we discussed today. Another way, it may be impact load acting on the gear teeth or pinion teeth. Now, inaccuracy of tooth profile, errors in tooth spacing, appropriate spacing is there, it won't be a problem. Misalignment between bearings and elasticity of the parts. These are the things. Okay, these are the things creating, I mean, very difficult to track the dynamic force. Okay, now the last one. Okay, okay, stop here. Okay, please give me, if you permit, I can complete this is, we'll do it later. Okay, it's okay, I stop it here. We'll discuss on Monday. Up to, I will share you the video, today video, and yesterday video I didn't post you. I thought I forgot it. I do it now. Yeah, please stay back in the meeting. I come to home screen. I want to see how many students are there. Yeah, please go ahead. If you have any doubts, please go ahead.
No doubts, sir.
Okay, but I would like to check this chat box because somebody maybe written something. Yeah, okay. We try to complete gear topic by coming Tuesday. Okay, sure, we have to complete Tuesday, and we will start next week. We have to complete this chapter, and we have to go through bearings. That is my target, because before midsum, I mean, for midsum we have to complete at least 3 to 4 chapters. 4 chapters we have to complete. Okay, okay guys, thank you. Kalyan?
Yes, sir.
Okay, I tried my level best the screen sharing video, using screen sharing video for recording. I
Yes.
hope that it will come perfect. Once I will take the data, I will share you the video, post in the video and the LMS. Okay.
Okay, sir.
Okay. Thank you guys. Have a nice weekend.
Thank you.
Thank you, sir.
Thank you, Jayesh.